Hello, everyone, and welcome to another class of Matter and Sustainability. Today, I'm going to explain to you the nomenclature of alcohols, aldehydes, and ketones. Well, alcohols are common substances in our lives. You can find them on beverages like wine, beer, etc. You can find it in pharmacies, in the rubbing alcohol that we can buy to clean something. Also, a lot of personal care products or hygiene products contain glycerin, which is a hydrating agent. And also the carbohydrates that are part of many foods. We burn carbohydrates to get energy, etc. Have this functional group of the alcohols. Alcohols contain the group OH in their structure. As you can see here, the R represents any alkyl chain, that is a chain of hydrocarbon. And when you see the OH connected to a carbon, you have to say it's an alcohol group. So here in this drawing, in this structure, you can see inside the red circle, the alcohol group, and inside the gray square, the alkyl chain. Alcohols can be classified as primary, secondary, or tertiary, depending on the number of carbon chains that are attached to the carbon that contains the OH. For example, here in the left, we can see a primary alcohol, where the carbon that contains the OH group is connected only to one other carbon chain, okay, the R here. When this alcohol group or the carbon of the alcohol group is connected to two R's or two chains, it's a secondary alcohol. And the tertiary, as you can see, contains a connection to three different alkyl chains. So depending on the number of alkyl groups, directly connected to the carbon that contains the alcohol group, it's the primary, secondary, or tertiary classification. So how can we name these alcohols? So let's begin with saturated alcohols. These are compounds that all of the carbon-carbon bonds are single bonds, okay? No double bonds, no triple bonds. So as we always do, we identify the longest continuous carbon chain, and we will use the name of that carbon chain as the parent hydrocarbon. And we have to change the ending to the name, to the ol ending, OL ending. So for example, methane ends in ane because it's an alkane. But when we have an OH substituting one of the hydrogens, the methane changes to methanol. Okay, the ending has changed. The same for ethane. Ethane has two carbons, but when one of the hydrogens is substituted with an OH, we change to ethanol, okay? So, when it's necessary, we have to indicate the position of the OH group with a number, as we did before with the substituents, for example, methyl, propyl, etc. So we will always try to give the alcohol group the lowest possible number. So here we have propane, the normal alkene, but when we have the OH group at the end, in one of the extremes of the molecule, we will call it 1-propanol. But when we have the OH in the middle, for example, in the second carbon, we have to call it 2-propanol. So these two are isomers of the same formula, of the same alcohol, but they have a different connectivity. So that's why we have to specify 1-propanol or 2-propanol. So when we have two or three or more alcohol groups attached to a hydrocarbon, we have to call them diols or diols, trials, etc. And we indicate with a number the position of each OH group. So here we have 1, 2 ethane diol. Okay, as you can see in the carbon 1 and the carbon 2, we have OH groups. So we have to call it a diol. And here we have a one with 3. 1, 2, 3, propane triol, okay? And here we have a cycle, for example, cyclopentane, but with a diol, no? This cis part is something that we haven't seen, but let me explain it very quickly. It is also related to isomerism, but the cis compound means that both functional groups, in this case, the red ones, the OH, are pointing up, let's say, or down, but both groups are pointing outside the plane in the same direction, okay? Both up or both down. In the other type of isomer, the trans isomer, one group goes up and the other goes down, or vice versa, but they are facing opposite sides, let's say, of the plane that forms the ring of cyclopentane. Okay, just to let you know this cis or trans thing. We're gonna see that later on when we see oils and fatty acids. So here we have a cis 1,3. We indicate the position of the OH groups in the cycle. 1,3 cyclopentane diol. Okay. When we have double bond, when we have alcohols, but with double bonds, in this case, unsaturated alcohols, I have to change this here from saturated to unsaturated. At least one double bond or triple bond between the carbons, okay? So the ane ending from alkane has to change to the in or ine, as we did before in the alkenes and alkynes. So you must give preference to the alcohol group over the double or triple bonds. So the numbering will reflect that. The numbering has to favor the OH group. So here we have a simple compound, 1-butanol. But when we have a double bond in this butanol, we have to give the lowest possible number to the alcohol group. So 1 will be 1 for the OH group. And then the double bond starts at the second carbon. So it will be a 2-butene. So you change the ending from butan to butene. And then we interrupt that with this 1-ol to specify the position of the alcohol. So 3-butyne 1-ol has the same pattern, right? So we give the lowest possible number to the OH, the first carbon. And then we indicate, we change this part of the name of the parent compound. Butane changes to butyne 1-ol. So here is a solved example of a more complex alcohol, and we will apply these principles. Okay, so here's a compound, and we're gonna see how to name it. So the first thing is to identify the longest possible chain. So as you can see here, the longest possible chain is made of 6 carbons. So the compound is a derivative from hexane. Okay, hexane means 6 carbons. Now the alcohol group takes precedence or preference. So here's the OH group. So the numbering will be better if we do it from right to left, right? Because it will take this number 2, which is lower than 1, 2, 3, 4, 5. Okay, so we numbered the chain from right to left, 1, 2. Okay. Now the other groups are the substituents of the carbon chain and are the following: 2-ol. Okay, we will use that. 3-methyl, which is just the CH3. And in position 5, we have the chloro. And we have a double bond. So we need to specify with this 5-ene, right? So the double bond and the alcohol group are indicated in the parent compound or the name of the parent compound. So hexane changes to 5-hexene because in carbon 5, we have the double bond. 2-ol because in carbon 2, we have the OH group. So finally, we put before that the name of this or the rest of the substituents in alphabetical order, as we did when we named other compounds. So the final name will be 5-chloro, 3-methyl, 5-hexene, 2-ol. Okay, so here you have 3 exercises, 3 different structures that you will have to apply the same principles, giving preference to the OH group, numbering in such a way that you give it the lowest possible number, and then name the other substituents and include the double or triple bonds in the ending or middle part of the name of the parent compound. Okay. So here we have 3 different structures. One are aliphatic or cyclic. Okay, and what about aldehydes and ketones? These compounds have a lot of different applications. For example, they can serve as a biological preservative to preserve like tissues in a lab or in forensics, etc. Maybe you have used this polish remover or nail polish remover to remove the polish from your nails. For example, some types of oils in almonds are aldehydes, and in perfumes you can find compounds like this one, this acetophenone. So aldehydes and ketones are very similar because they have this carbonyl group, okay, this carbon atom with a double bond to an oxygen. So here you can see the basic structure of an aldehyde and a ketone. So as you can see, the carbonyl is present in both types of compounds, this C double bond O, but the main difference is that aldehydes, this carbon is bound to 1 hydrogen at least, okay? But ketones are bound to 2 different alkyl chains or hydrocarbon chains, okay? Aldehydes just, well, they contain this hydrogen. This is the main difference, okay? So aldehydes and ketones are very abundant in nature. Many of the fragrances and flavorings of fruits, vegetables, etc., come from this type of compounds, aldehydes and ketones. Also, a lot of vitamins, dyes, and hormones that we produce as animals are of the type of aldehydes and ketones. And basically, all of the carbohydrates have these functional groups in their structure. Aldehydes and ketones, for example, glucose, which is the most common sugar that we process in our cells, is a type of aldehyde with a lot of alcohol groups. And fructose, that is part of sucrose or sugar, it's a type of ketone. Okay, so how can we name aldehydes and ketones? Again, we apply the same principles. We identify the longest continuous carbon chain. That will be the name of the parent compound. And we change the ending now to al, A-I-A-L, for aldehydes, and to one for ketones. Okay, so we have here propane, which is the basic alkane. When we have this aldehyde functional group, we call it propanol. Okay, propanol. And we have this carbonyl group in the middle of our 2 carbon chains. In this case, ketone, we call it propanone. Okay, the ending has to change depending on the aldehyde or ketone nature of the compound. So what if these aldehydes or ketone have 2 or more groups? That it can happen, right? So we call it as diols. We call it diols or diones. Okay, so here we have 1,5 pentanediol and 2,4-hexanedione. Okay, we need to specify the position of these carbonyls, and with the prefix, with the Greek prefix, we indicate the number of that functional groups. So what if we have a more complex case? What if the molecule has aldehyde groups and ketone groups and alcohol groups in the same molecule? So we need to apply a different criteria. So the idea is to identify the functional group with the highest priority, okay? When we identify that, we use the suffix or the ending of that functional group in the name. And the rest of the groups, the other groups, will be like substituents, and we will use the prefix. Okay, let me explain the table. So if you find a molecule that has aldehyde groups, ketone groups, and alcohol groups, the highest priority has to be given to aldehydes. So the molecule will have the ending al, okay, like pentanal, hexanal, okay? And the rest of the groups are going to be named using the prefix. So the ketone group will be named oxo, and the alcohol group will be named hydroxy. A way to remember this priority scale, I think it can work if you remember the alone owl, the alone owl. So as you can see in red, the highest priority will be the aldehyde, so that alone. The own is for ketone, and the owl, it's the ending for alcohols. Okay, so it works for me, maybe it can work for you. So again, you identify the group with the highest priority, and that group will have the ending, or you will have to use the suffix in the name, but and the rest of the compound or the rest of the functional groups will use the prefix, okay, not the suffix. So let's see an example. When we applied all of the concepts that we have been seeing. So I will solve this example. So as you can see, there's a hydrocarbon chain. There are many groups, the OH group, the ketone group, and this triple bond. Okay, so how can we decide? How can we name it? We need to identify the group with the highest priority. Remember the alone owl, aldehydes have a higher priority than ketones, and ketones a higher priority than alcohols. So in this case, the ketone will have a higher priority than the alcohol group. So the molecule has to end in -one, not in -ol. Let's see. So the longest carbon chain, it's made of 5 carbons. So the compound is a derivative from pentane. Okay, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So there's a triple bond. We need to take this into account. So the name has to change from pentane, the alkane, to pentyne, the alkyne. Okay, the triple bond gives this -ine ending. Okay, so now the ketone group takes precedence. So the lowest possible number for the ketone group is obtained when you number the chain now from left to right. So it will take the number 2. Now the name has to change, as I told you before, has to change from pentyne to something like pentynone, okay? And the alcohol group, because it has a lower priority, will be given the name like a substituent hydroxy, okay? So finally, the name ends being 5-hydroxy, because it's in the carbon number 5, 5-hydroxy, 3-pentyne, 3 because the triple bond starts at the carbon number 3, and 2-one, it's indicated that in the carbon 2, you have the ketone group. So it's a 5-hydroxy, 3-pentyne, 2-one. All right, so you can practice these ideas solving the following exercises. Remember, you apply the same ideas, identify the longest carbon chain, give priority to aldehydes, then to ketones, and then to alcohols. Include the double bond, the double or triple bonds of carbon-carbon, the carbon-carbon double or triple bonds in the name. So pentane to pentene or to pentyne. Okay, and indicate the rest of the functional groups as substituents: hydroxy, oxo, methyl, propyl, chloro, bromo, etc. Okay, so that will be all for this class, and we're gonna do a lot of exercises, but start doing the exercises of this presentation. Thank you very much, and see you in class.